So hello again. So so in this lecture we are going to do a slight change of pace, right? So far we have been looking at what are called value function based methods, right? And if you remember way back in the beginning, I was telling you about how you can use value functions because they are unique, but you could potentially search in the space of policies also directly, right? So what we are going to do today in this lecture is look at what are called policy gradient algorithms, right? So let's step back and look at what we are doing here. So in policy search, the policy gradient algorithms fall into a larger class of algorithms called policy search methods, right? So in policy search methods, what we do is that instead of maintaining a value function, right? So maintaining a value function and then having the policy defined implicitly as epsilon greedy or softmax on that value function, right? We will basically define the policy directly, right? We'll just say what is the probability of taking action A in state yes. We'll explicitly store this, right? We'll explicitly store the probabilities of taking action A in state yes, right? Instead of saying that pi of A is basically coming from some e power q of s comma A divided by summation e power q of s comma B, right? So instead of doing this, right, so we don't have the q function anymore. I mean, we could still use some kind of a parameterization like this, right? But it will be something like e power theta A, right? And this is e power theta B, where theta A and theta B are some kind of parameters that describe the preference that you have for action A, right? Theta B is the preference that you have for action B, and so on and so forth, right? So so we will basically maintain theta A's and theta B's instead of maintaining QA and QB, right? QSA and QSB, right? Apart from this, you could use other kinds of explicit representations for pi of A. So you could just say pi A of S is some rho A, right? And then you can say that summation of rho A prime is equal to 1 and individually rho A prime greater than or equal to 0 for all A prime. So this is basically like a multinomial, right? If this could essentially be a multinomial distribution, or we could just basically say that I'm going to keep this as some kind of a Gaussian, right? With a thing where I have mu comma sigma, right? Mu s and sigma s are the mean action and the variance of the action, and then A, this basically gives me the probability that I'm doing action A, right, when you are sampling from a Gaussian, right? There are many ways in which I can directly represent a policy like this. So why would we want to represent the policy explicitly as opposed to going through the value function? Okay, so there are multiple reasons for it, right? The first thing is actually something that might be surprising, is that sometimes the policy directly yields a simpler description than the value function itself. So for example, if you look at the problem of let's say you have a warehouse and you want to order some inventory in the warehouse, right? So you would like to place an order for a particular item. Typically the policy takes the form that if stock below some threshold theta, then order. If the stock falls below some threshold theta, then you place an order. So for learning this policy, all you need to do is learn this parameter theta. So what is the threshold? When the stock falls below that, then you have to order, right? But if you look at the value function, it can be a pretty complicated function of the stock level of item, so 1 to k, right? So if stock of I falls below theta of I, then order I, okay? So that will basically be how it will be. But there might be items that go from 1 to k, right? K items are there. So the value function itself could be some kind of a very complicated function of all the k variables, right? All the k items, right? whereas the policy itself can become something simple like if stock of I is less than theta of I, then order I. Right. So, that is one of the reasons why we would like to represent a policy directly instead of a value function, because it sometimes or yields much simpler descriptions than going from the value function definition. Okay. The other thing which is important is we already looked at parameterized representations for the value function, right. So, where we are saying that okay, I have q of s comma a, but it is represented using some parameters theta, and then we talked about how these parameters can come from a neural network and where you get deep Q learning, and before that we had various forms of linear function approximators and all that, right. So, one of the things that if you remember I was talking about in the context of all this linear function approximation and deep learning and so on and so forth, is that it is very hard to ensure that your learning actually converges to the true Q function, right, because of this whole function approximation, non-linearity, moving target, all of these problems, we are not sure that we can get it to converge consistently to the optimal or the correct Q values. While in the case of tabular setup, it was all fine, right. So, in tabular case, we know that for sure it will converge, but as you also know, tabular cases really cannot generalize to real problems, right, real large problems. So, we have to go for some kind of a function approximation based approach, and when you get into this function approximation space, we know that these things do not work that well, right. The convergence is a little bit of a problem. On the other hand, most of the policy search methods, particularly policy gradient methods, are kind of gives you much better convergence guarantee, right. They are almost like any function approximation that you would do, in the sense that they give you convergence to some local optima. They guarantee convergence to some meaningful local optima, while that is not the case with value function approximation methods, right. So, therefore, policy search methods or policy gradient methods, algorithms are preferred in the setting of function approximation. When anyway the problem is so large and I am not able to represent things explicitly, I would prefer to go for approximations. Then policy methods are more robust, right. And another thing which I also have to mention is that when you are talking about continuous actions, right, you are talking about continuous states, you can have a function approximator and you can generalize, right. But when you are talking about continuous actions, you can't do that Q network idea, right. You will have to come up with other ways of representing a policy, right, with continuous actions. You can still use a Q function, right. I mean, let's not worry about the underlying mathematics of it, but you can still use a Q function where A is continuous, because you are just plugging in the A value to the Q function, so it is fine, right. So, just plugging in the A value to the Q function. So, it is like any other function that takes a real argument, right. So, you can take state and action as an argument to Q and it will return some value. So, you can imagine it being defined like that, but it turns out that value function based methods are notoriously hard to make work, right, with continuous actions, right. So, typically what you end up doing is you discretize this continuous action into bins and say that okay, I have this range of 0 to 1 and now I am going to divide it into 10 actions and I have picked between one of these 10 actions, right. So, instead of that, policy gradient methods allow you to actually keep the actions as continuous action, just like you saw in that example with Gaussian, right. So, I can actually make the probability distribution a normal distribution, so that the action can actually be ranging from minus infinity to plus infinity. So, this still does not matter, right. So, I can encode it as a distribution, right, and then so I can encode it as a distribution and then I can learn with that, right. So, policy gradient methods behave better. In fact, they are the methods of choice nowadays if you are going to use RL with continuous actions, particularly in places like robotics and so on and so forth. So, it makes a lot easier to use policy gradient methods. So, the third part is something to do with an approach called partial observability, right. So, what is partial observability? Partial observability is when you do not have access to the full state yes, right. So, I do not have access to the state yes. What I have is some function of yes that I am able to see, right. So, how does this look like? For example, in the case of Atari games, right? So, you don't really have access to the true state, right? There is a simulation state that is happening inside the game, right? So, that is some kind of what's called a RAM state, right? That tells you what are all the variables that are now used and how is the display constructed, which direction is the ball moving, which direction is your opponent thinking of moving. All of these things are there in the state internally, because that is what is needed to run the simulation. But what you get is what is rendered on the screen, right? So, what you get to observe is some function of this internal state, right? And we try to kind of make it better by saying that we will take 4 frames together. So, this function of the state f of s that we are talking about here essentially is this 4 frames concatenated together in the context of Atari, right? So, some complex function of the underlying. So, this is called partial observability. In fact, in many real problems, partial observability is given, right? So, we talked about how you can take a non-Markov state and make it more Markov by adding history, by doing a bunch of other things. So, all of that are methods to handle partial observability, okay? And the thing with policy search methods or policy gradient methods is they are typically more robust to partial observability, the pure policy search methods, because they do not usually use a notion of value function. If you remember, if you use the notion of a value function, you are tying it to the notion of a state, right? So, I am talking about q of s comma a or v of s, and if I do not estimate s properly, then I have a problem, right? So, therefore, policy search methods which do not directly rely on a value estimate are more robust to partial observability, okay? So, you could do multiple ways. So, the first thing is to do what is called direct policy search, which is essentially just search around in the space of policies using some kind of a heuristic, could be some local search methods, or the more popular way of doing this direct policy search is to use what are called genetic algorithms, right, or evolutionary methods, right? Genetic algorithms or right. So, I will not be going over evolutionary methods in this course, right. If there is ever going to be an advanced RL course, we will see all of these in that. But I am just giving it to you as a potential direction you could look at. So, there is this whole bunch of approaches that directly search in the space of policies, right. The other class of algorithms that we are going to talk about more today are what are called policy gradient approaches. Policy gradient approaches essentially, as you can imagine from the name, right, form some kind of a gradient of your performance, right, with respect to the parameters that you use for representing the policy, right. So, if you think about value function based methods, we are using some kind of a gradient of the TD error, right. We are using the gradient of the squared TD error in order to give you the direction in which to change, right. And likewise, we are going to come up with a performance metric, and we are going to take the gradient now, and we will use that for updating the parameters, okay. So, that is basically the setup here. So, let us take let's start taking a little bit of a deeper look. So, the policy that we are defining now in these policy gradient approaches is that the policy is going to depend on some kind of parameters theta, right. So, I already gave you 3 examples, right. So, the first example was where we said you have some preference called theta a, right. For each action you have a preference called theta a, right. So, that is one way of doing it, which we say that probability of the action given S is equal to e power theta a divided by summation e power theta b, right. This is one way of defining it. The other way I said that pi of a given S equal to some rho a, right, and summation over b of rho b equal to 1, and individually rho b is greater than or equal to 0 for all b. This was the other way of doing it, right. And then the third way I said was pi of a given S is equal to some kind of a normal distribution of a given mu s comma sigma, right. So, this is essentially for the top 2 or for discrete actions, right, and this is basically for continuous actions, right. So, the actions in the third case range from minus infinity to plus infinity. In the first case, first 2 cases you have some set of actions, right. So this is your usual softmax kind of a rule, and this is a multinomial, right. So the parameters theta in this case are actually theta, right. So theta a1 to theta ak are my parameters theta. In this case it will be rho a to rho k will be the parameters theta, right. So it will be rho as, okay, yes, has to be an yes everywhere, right, because I am talking about the probability of taking the action A given yes. So there will be yes everywhere, and likewise here the parameters will be mu s and sigma s, right. So this will be my vector theta, this will be theta, and this will be theta, okay. So this will basically, when I say the policy depends on some parameters theta, so I mean one of these kinds of parameterizations, right. So either like the softmax kind of a thing, or this, or what else? It could be the weights of a neural network, right? I could have a very complex neural network, and the output of this, instead of being value functions, could just be these kinds of probabilities, okay. So because now I am predicting probabilities, I will have to figure out appropriate ways of training these neural networks, or finding out these parameters theta, right, so that I am actually modeling the probability. So how do I do that? So we will have to figure out how we are going to get that, right. So the goal here is, the main idea, key idea here is that I am going to modify these policy parameters directly, right, instead of estimating action values. So I am going to directly change these theta, right, instead of saying that I am going to update action values using my TD error, that somehow gives me an estimate of how better it is to do one action over the other, and then I am going to use literally I am using the policy as a way of sampling transitions so that I can make my action estimates better, and hence make my policy better, right. So that is how we have been setting up this whole thing so far, right. And now instead of estimating the action values, I will directly modify the policy parameters. So we will do this for a while, and after that we will say that, hey, look, there is something good for doing this policy gradient approach, there is something good with doing action values. So we will combine both and come up with a new class of algorithms called actor critic method. So that will be the next set of algorithms we look at. Right now we will just limit ourselves to policy gradient approaches, okay. So the first thing that I do is, given my theta, right, given a particular parameter theta, I am going to define a performance function, right. I am going to define a objective function which we call j of theta. J of theta is something like the value function, but it is basically the performance of the policy as a whole, right, for the particular value for theta. So whenever I change the value of theta, I am actually changing the policy itself, right. So for a particular value of theta, so for a particular policy, right, if I fix my values of theta, I fix my policy pi, right. So for my particular policy pi, j of theta gives you some kind of a performance metric, right. So first thing I have to do is I have to define this performance metric. So in some sense you can think of this as the expected total reward that you will get, or in some sense you can say expected GT as well, right. So either RT, or you can say expected total reward or expected total return is what I am going to try and maximize, right. So given the policies pi is fixed, right. So what's some sense the expected total reward that I am going to get, okay. And then what I do is I find the gradient of this j of theta, right, with respect to this policy parameter theta. So what does this mean? If I change theta slightly, how does my overall performance metric changes, right. And then I am going to take a small step in the direction of the gradient, okay. So let's see if I can do this very roughly. So normally earlier when we had this kind of a, right, so this I'm just drawing it in a three-dimensional figure, right. So this is my you can think of this as theta 1 and think of this as theta 2, right, and this is basically the error in whatever function I am predicting, right. So error which would be, in some sense it could be just the f minus y hat or something, right? F minus y hat square could be the error. And normally what we do is we try to find out, take a point somewhere here, you try to find out the gradient, you try to find out the gradient. So it's descending in this direction, therefore you look at this direction here in the theta 1 theta 2 plane, and you say that okay, if you move in this direction in theta 1 theta 2, then you are likely to decrease the error, right? So that's basically how we thought of gradient descent earlier, right? So you have a function, and then you look at the direction of steepest ascent, right? Look at the direction, I should put it that way. Look at the direction of steepest ascent, and then you move in the direction opposite to that, so that you are moving closer to 0, right? So that's basically closer to the minimum error. So that's how we had it earlier. Now in this particular case, what we do is we are actually talking about we are talking about not about error, but about j theta, which is on the performance part, right? So it's going to be something like this, right? So it's going to be like an inverted bowl, if you will, because I'm looking at that part of the curve where I want to have maximum performance. And now what I do is I look at the direction of steepest ascent, and then I actually move in that direction, right? I move in that direction in my theta 1 and theta 2, so that I am moving towards the maximum, okay? So these kinds of approaches are called gradient ascent approaches, because I am moving in the direction of the gradient, not opposite to the direction of the gradient. So when I am doing opposite to the direction, they call them gradient descent, right? So far you have looked at gradient descent, whether it is in deep learning or other forms of ML approaches, or here typically you look at gradient descent. So this is probably the first time you are looking at an algorithm that is a gradient ascent algorithm, right? So where you are moving in the direction of the gradient so as to improve the performance over time, right? So you start off with some theta 1 theta 2 setting, and then you estimate what the performance is, and then take the gradient of the performance, and then take a small direction in the step of the gradient so that improve the performance. So why a small step? Because it's still stochastic gradient, just like in the function approximation case, the value function approximation case, I'm still doing stochastic gradient optimization here. So I'm doing stochastic gradient ascent. So that's basically why you take a small step in the direction of the gradient. Okay. Now I'll try and make these things more concrete, right? But I'll do that in a simplified setting. Let's go back and talk about the immediate reward setting, where we only had the explore exploit problem, right? The multi-arm bandit setting, right? Not even the contextual bandits. I'm just going to go back to a very, very simple setting of the multi-arm bandits, and I'll tell you what are all the essential components that are going to play a role. And then later on, when we develop the full theory for policy gradient methods, I'll come back and tell you how this simple multi-arm bandit case is a special case of that, okay? So if you remember the multi-arm bandits, so you have n action, right? And so you have to learn to select the action so that you get that arm with the highest expected reward, right? So each selection results in some rewards, right, with noise. So I mean, it could be like a you get it or don't get it kind of a noise, or it could be like a normally distributed reward function that you're going to get, just like you did in the simulations already, right? In the first programming homework, you would have seen that you're talking about simulating bandits, where the reward for pulling an arm comes from some Gaussian, right? So the Gaussians have different means, and the idea here is to actually figure out which arm to pull so that you get the maximum expected return over time, right? So that's basically what we said for the bandit case setting, right? So that's the idea here. And so a couple of notational things I'm going to use. First of all, I'm going to assume that there is some parameter, set of parameters theta, right? And pi theta a is the probability that with which I'll select action A when my parameter setting is at theta. So theta is some value, right? So when a parameter setting is at theta, what is the probability I'll select action A? So that is pi theta a, and q star a is the true expected value, right, of the reward for taking action A. Just like we have Q star SA is the optimal is the maximum expected reward that you can get, right, and likewise Q star A is the expected reward that you can get for pulling action A. So, if you keep pulling action A repeatedly, then Q star A is the true expected reward for pulling action A, right. So, you would have an estimate of this expectation as you are learning, right, like we normally do, and sometimes the estimate may be above the Q star, true Q star, sometimes the estimate may be below the true Q star, right. Just to give you a sense, this Q star A will be the mean of the Gaussian, right. When you did your simulation experiments, when you did your programming assignment, you would have generated first the mean of the reward, right, from a 0 mean Gaussian, you generate the mean of the reward, and then you use that as the mean of a new Gaussian, right, which will then keep giving you the rewards whenever you pull that action A, okay. So, that mean that you have for action A is your Q star A, right. So, the Q star A is essentially given by is the mean of the action when you are doing the rewards as we did in the programming assignment, okay. So, this is the setup. So, my expected reward, now if you think about it, right, my expected reward, right, what is the total reward I am going to get is, hey, if you pull action A, if you pull action A1, right, Q star A1 is the reward that you are going to get, that is the expected reward you will get, right. If you pull action A1, Q star 1 is the A1 is the reward that you are going to get, but I am going to pull A1 only with probability pi theta A1. Likewise, I could pull A2, A3 all the way up till AN, and so that basically is Q star A1 into pi A1 plus Q star A2 into pi A2 all the way to Q star AN into pi AN, and pi here is given by pi theta, okay. So, that is basically my expected reward. So, my performance measure is basically given by this summation over A of pi theta A Q star of A, right. If you think about it, it is somewhat like the value function, right. The value function, what would you say, it is pi of S comma A into Q of S comma A, right. Pi of A given S into Q of S comma A, it gives me the V of S. So, this is something similar, there is no S here, therefore, I just take pi of A into Q of A, that gives me the value, total value, okay. So, that is basically how I define my J theta here. Now, we have to think about what does it mean to say I am going to take the gradient of this and so on and so forth. So, let us look at the next one, okay. So, let us look at how we are going to compute the gradient of this performance, right. So, we have to compute the gradient with respect to the parameters theta only. So, this is the expression, and now I take the gradient of this with respect to theta. Now, Q star A is a function of the bandit itself, right. It does not depend on what policy I am following. What does Q star A tell me? Okay, if you take A, this is the expected reward you are going to get. So, that does not depend on theta. So, when I say I am taking the gradient with respect to theta of J theta, I am really, this thing can be skipped, I am only taking the gradient of pi theta, okay. So, I am going to take the gradient of pi theta of A, depending on the form in which pi theta is, this gradient will look different, okay. So, now I am going to come here. So, this basically now is Q star A. See, originally for doing this expectation, right, let us go back and think about what we would have done for estimating this expectation, right. For estimating this expectation, what is the problem? Suppose I am going to do this, right, I am going to find the expected value of R of t and I want to estimate this expected value. I do not know Q star, right, I do not know Q star. So, I can't estimate this, I can't just compute this sum, right, I will have to do this somehow through sampling. So, how will I do this? I will basically fix my pi theta, right, and then I will sample repeatedly from pi theta, right. So, t equal to 1, t1, t2, t3, blah 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 all the way up till some tn, right. So, I will be taking some n, capital N samples, right, with after fixing my pi theta. So, what is going to happen? I am going to get R t1, R t2 all the way. I will just make it simpler, right, I will just use R1, R2, it makes my life a lot easier, all the way up to Rn, right, and I would have chosen A1, A2 up till An, right. Remember, I have n actions, right. Okay, so let us not confuse this n and that n, that is a small n, this is a capital N. So, capital N is the number of samples I have drawn. right. So, I fix pi theta, then I select action A1 at time t1, I am going to get R1, I am going to select some action A2, this A2 is basically the action I select at time t2, right, not this A2, okay. Then I will get R2 and so on and so forth, I keep doing this, right. Now, how can I compute this expectation? Right. So, these actions were sampled according to pi, right. So, what I can do is I can basically add Ri and divide by 1 by n to give me a estimate of j theta, correct. Why am I able to do that? Because I am sampling these Ri's according to pi theta, right. So, instead of taking the expectation of q star according to pi theta, I can take the average of all the R's that I have taken by sampling according to pi theta, and that gives me an estimate of j theta, okay. Now, I take the gradient, right. So, what happens is I have this function now, right. So, once I take the gradient, I have this function which is sum over a of q star a into gradient pi theta of a, right. I am taking the derivative of pi theta a. Now, this whole nice sampling thing that I had goes away, because earlier this was I could treat this as an expectation, right. I could treat this as an expectation of q star under pi, and I kind of approximate that by taking the rewards, right. So, I have done that here. So, that gives me the expected value j theta, but I can't do that anymore. So, to convert this into an expectation, right, I multiply and divide by pi theta, right. So, now this guy I can write as expected value under pi theta of q star a into right. This thing becomes the expected value under pi theta of q star a into gradient of pi theta by pi theta. So, this ratio comes in here, and my pi theta just now comes with the expectations, right. I hope that makes sense to people. From here I have converted this into an expectation. This should kind of remind you a little bit of what we did with important sampling. The expressions look similar, but the reason why we are doing it is slightly different, right. So, basically I have done this now, right. And now I have converted this gradient now by doing this multiply and divide. I have converted that into an expectation, okay. Now, I can approximate this expectation, right, just like we did here. This expectation we approximated by taking samples. So, this expectation, because I am sampling according to pi theta, I can approximate it, the same thing I did here, right, just like what I did here. I have n samples that I draw by fixing the parameters at pi theta. So, I choose a1 to an, right, according to pi theta, and then I get r1 to rn. So, now what I do, instead of averaging ri like I did in the first instance, right, I averaged ri. Instead of averaging ri, what I am going to do is I am going to average ri times the gradient of pi theta divided by pi theta, this ratio. Does that make sense? So, instead of taking the average of Ri, which I did to get this, because I have to do this, the expectation is now of q star a into gradient pi theta by pi theta, right. So, because of that, I am going to take the average of Ri into gradient pi theta by pi theta, where I am going to use the actual corresponding a, the probability of that here, to get the likelihood ratio, what is called as likelihood ratio, and take the average, and that gives me a approximation of the gradient of j theta with respect to theta, okay. Just to remind you, this is essentially expectation according to pi theta of q star of a. Now, I do not have to quite do it in this manner, right. I said you fix the parameters for n time steps, and then you compute the make an estimate for the gradient, and then use that to change the parameters, right. So, once I compute this gradient, what will I do? I will add some alpha times this gradient to my current value of theta to move it in a direction where j will increase, right. So that's basically how I handle it, but I don't have to do this in this way, right. I don't have to draw n samples, take the average and do that. That's a whole nice advantage of all the stochastic gradient computation that we do. So we can implement it as a proper incremental version. So what do I do in that case? Instead of saying that I'm going to compute the gradient over multiple samples, I'll say I'll just take one sample. Okay, at time t, I'm just drawing one sample. So I'm going to take at time t, I'm going to take AT by sampling from pi theta t, right. So I sample from pi theta t and I get my AT, and then that's going to give me an RT, right. Just this one interaction I'm going to take, right. Now I'm going to say that the parameter change. Right. So, I am going to say basically what I am going to happen is delta t plus 1 is equal to delta t plus alpha times theta t alpha times delta theta t, right. So, this is basically what or rather not even alpha, I am sorry. So, theta t plus 1 is equal to theta t plus delta theta t, which is the change that I am going to make to theta at time t, right. That I am going to say is alpha times RT, which is the sample I got, times this likelihood ratio that I had for the action taken at time t. That's basically just one action selection. And what is the nice thing about the reinforced paper by William from back in 1992 is that this whole idea of stochastic gradient descent or stochastic gradient ascent wasn't really that ingrained back then. So he came up with this, one of his earliest results, to show that, hey, I can do this provided my step sizes are small enough, provided my alpha step sizes are small enough, right. Then even though I am doing this on an incremental version, right, so where each sample of the gradient can potentially be arbitrarily wrong, right. So each step that I take, right, could be in arbitrarily wrong direction, because the expectation is what gives me the right gradient, right. But he showed that even if you do this, as long as your alphas are small and some other conditions are satisfied, that you will eventually converge to the true maximum, right. So that's something that he showed back then. And remember, this was in the early 90s, right. So neural networks were still popular. So in fact, original reinforced derivations and everything assumes that you are actually using a neural network for your policy representation, but it was a cool piece of work back then, right. So William showed that this will actually converge to the true maxima, right, or close to true local maxima, right. So not the global optima. If the surface, as you know, with any kind of gradient approaches, if your surface is many optima, then it will go to the nearest local optima, right. They showed that it can converge. So that's the cool thing. But there's yet another cool thing here, right. So what is that? So since we look at pi theta by theta, right. So if you think of this as those gradient things that you're doing, this is basically the gradient of ln pi theta by rho theta, right. So instead of looking at it as pi theta at divided by pi theta, you can think of it as ln pi theta by d theta. So this ln thing allows us to simplify a lot of the gradient computation, right. So if you think about the various forms that we talked about here, right. So if you take the ln, now this will become a difference, right. So that makes it easier. You take a ln, the e power thing goes away in your Gaussian representation and all that, right. So many of these kind of commonly used policy parameterization can become potentially much simpler when you're talking about taking the logarithm of the probability, right. But that's a nice thing about it. So the fully incremental version of reinforced can be basically written as delta theta t, which is the change in each step theta, is equal to alpha times the reward that you sample at time t times the partial derivative of ln pi of at divided by rho theta, right. So that's basically the simple incremental version of reinforced, and it's turned out to be pretty influential today, because any kind of stochastic activation function that you are coming up with, right, it turns out that doing the back propagation becomes a little bit of a tricky thing. So what people have been looking at is this kind of this reinforced trick, where you multiply and divide by something else, and then you get this. So you basically use the ln, right? Instead of using the regular back propagation ideas, you use the dou ln by dou theta of the probability of selecting that sample, right? Use that in order to compute the gradient, right? Now this becomes a true estimate of the gradient. So people call this a reinforced trick, and quite often in a lot of this modern neural network papers, they use this reinforced trick and then they call it, hey, we are doing reinforcement learning. This is not quite right. Remember, reinforcement learning is all about learning from evaluation and not from supervision. But sometimes what people do is they use the reinforced trick even if they have supervision, because they are using some kind of a stochastic activation. To get around that, they use this, and so it's not quite kosher to call it reinforcement learning. It's perfectly all right to use the reinforced trick to make the updates in the deep networks. Right? I'm not going there. Okay. So that's the basic reinforced setup, right? But then Williams thought about a few things, right? And then he came up with something called reinforced with baseline, right? And this is actually very important, as we'll see later, because many of the modern variants of all these policy methods and these policy gradient methods and the actor critic methods, which is like this mix of value based and policy gradient methods, right? All of these use this notion of reinforcement with baseline in order to stabilize the learning. Okay, so I'll tell you what the original motivation was for Williams. Right, suppose I get and reward RT. Right, remember that RT is just some scalar. Right, I don't know if RT is good or RT is bad. Correct. I don't know if RT is good or RT is bad. I would really like to have some kind of a reference to which I can compare my RT to know whether it is good or bad. For example, if all my actions have a reward of -5, then a reward of -1 is good, correct? But if all my actions have a reward of 1, then a reward of -1 is bad, right? So this whole idea of this, just getting this numerical feedback, right, means that I need to have something to compare it against. So if all rewards are negative, an R of 0, right, is actually a good reward. So what Williams said is, okay, let us come up with this idea of a baseline for the reward, right? And if you're above the baseline, we'll consider you as a good reward. You're below the baseline, then we'll consider you as a bad reward, right? And another advantage is, you can think of this, if you think of this baseline as like the average of all the rewards that you have gotten so far, right? I mean, the baseline can be anything. I can just arbitrarily fix my baseline to be 0, right? So the only thing that I need is that my baseline BT should not depend on AT, right? My baseline PT should not depend on AT. So I shouldn't use a different baseline for different actions, right? And likewise, I can also have my learning rate change with time. So my alpha T should not depend on RT, right? So I shouldn't. So if I have a high reward, I shouldn't use a high learning rate. If I have a low reward, I use a low learning rate. That means I'll be introducing bias, right? Suppose I have a learning rate of 0.2 when the reward is positive and 0.1 when the reward is negative. That is like saying that I'm sampling the positive reward 2 times compared to the negative reward, right? I'm sampling it twice as more often than I'm sampling the negative reward than the true probabilities, right? So that is basically messing with the sampling distribution in some sense. Therefore, I don't want to have different learning rates for different rewards. So take it on faith now, right? So I'm not going to get into the full nitty-gritty details as to why that is needed. So alpha T should not depend on RT, and the baseline should not depend on what is the actual action you take, right? Because the baseline should if it depends, if it's just going to change with what action you take, then that's not allowing you to compare one action with another action, right? The baseline should be common across the actions, right? So the usual baseline you use is basically the average of all the past rewards you have gotten, right? So now if I'm going to take the actual sample I get and subtract away the average, right? So it's only be looking at the deviations. So automatically I am kind of stabilizing the magnitude of the changes that I will make, instead of saying that, okay, that R is 5, but the average is 2, right? That means that then the actual magnitude of the change that I will be making is only proportional to 3. So kind of an average as just this, right? I'm actually making the updates more stable, right? So there are multiple advantages to using this kind of a baseline, and so the typical baseline that we will use here is the average reward. Okay, So, what final just a few more eligibility, I mean few more terminology things. So, this ratio, right, the differential of the ln pi by the with respect to theta is called the characteristic eligibility. So, it has a similar motivation as the original eligibility trace that we talked about, right. It basically tells you how much should a particular parameter theta receive the reward, right. How much eligible is a particular parameter theta for receiving the reward. So, that is why it is called the characteristic eligibility, and BT is called the reinforcement baseline, right. So, typically it is some constant that we expect the reward to be, or it could be just the current expectation of what the reward is, the current mean of the rewards. So, if your action has a reward higher than the mean, then you take it more often. So, that will also keep pushing the mean up, right, and so on.